If I can't picture it, I can't understand it. Albert Einstein. Welcome, students. Today, in Dynamics of System of Particles, we discuss Center of Mass Reference Frame, Part B, Energy Methods. In Part A, we have discussed how can we use Newton's law and momentum methods in center mass frame. Today's talk is based on how can we use energy method in center mass frame and where it will be advantages. Because on the last turn, we have discussed that to analyze a problem, sometimes a particular reference frame gives advantage. Actually, how we select the suitable reference frame depends on two things. First one, either in the problem it is mentioned to use a particular reference frame in the way that some quantities will be given in a particular reference frame or they will be asked in a particular reference frame. In such case, use that reference frame. But in some problems that is not so. But while solving the problem, we encounter some quantities which will become either too cumbersome to calculate or they will become impossible to calculate with the known methods. So, in such situation, we must seek such a reference frame in which either the value of these problem creating quantities become zero or will become known, or they can be easily calculated, or they become unnecessary in producing solution. In this way, center mass frame provides sometimes very simple solution. So let us understand qualitatively from a problem that we will take today as an example also. Here on a horizontal frictionless floor, two blocks A and B are placed. They are connected by a spring. And initially when spring was relaxed, a force F was applied on block B and is asked to find maximum extension in the spring. If we use this problem from ground frame or laboratory frame, what we know? We must know the time when maximum extension occurs and spring force as function of time. Only when we can calculate displacements of the block and by subtracting them, we can find the extension in the spring maximum. But knowledge of spring force as function of time and the time when maximum extension occur, that we can obtain from the knowledge of simple harmonic motion, and that we have not studied till so far. So we cannot do it. Again, after studying simple harmonic motion, we'll see that use of that ground frame is not simpler than the use of center mass frame. But how the center mass frame provides simplicity, we can understand only after discussing each and every aspect of that in detail. So let us begin with discussing about energy methods in a center mass frame. Methods of work and energy in center mass frame. What is the first idea? That is, in classical mechanics, mechanical work and kinetic energy depend on frame of reference, but the change in potential energy does not. That is very remarkable idea. The change in potential energy does not depend reference frame. We'll discuss it, but let us first come on mechanical work and kinetic energy. They are frame dependent. Why? Mechanical work is obtained by dot product of a force and displacement. A physical force is frame independent, but path is frame dependent. So mechanical work will be frame dependent. But kinetic energy, it depends on velocity, and velocities are frame dependent. So kinetic energy will also depend on reference frame. But what about potential energy? Potential energy are decrease in, actually, change in potential energy. Change in potential energy is what? It is accounted by work done by internal conservative forces when configuration of system changes. And when configuration of system changes, there are two important things. In configuration change, that is the path of the particles may be different from different reference frame, but the forces are conservative. They do not depend on that is, you can say, reference frame, because real forces are path frame independent. Again, they are conservative, so your work will not depend on path. So in this way, change in potential energy will be frame independent. That is very remarkable idea. Let us revise what quantities in energy methods depends on frame and what quantities will not depend on frame. First we take mechanical work. It is frame dependent. It depends on reference frame. From different reference frame, mechanical work will be different. Kinetic energy, frame dependent. Obviously, velocity is frame dependent, so kinetic energy of a system from different frame may be different. Change in potential energy, that is frame independent, and we have seen why it is. That is very remarkable thing. And another remarkable idea is what? Loss in mechanical energy is frame independent. Actually, loss in mechanical energy is converted to heat. How much mechanical energy is lost is converted into heat, and heat energy is frame independent. So loss in mechanical energy is frame independent if it is converted into heat. So that is frame independent. So that is what very remarkable ideas, and we have to remember them while solving problems. Kinetic energy of a system of particle and center of mass. Now you see, how can we write kinetic energy of a system of particle in center of mass frame? Actually, in any frame, total kinetic energy system is what? Kinetic energies of all the particles in that frame. But here, let us see in what we can do in center mass frame. Total kinetic energy of a system of n particles of masses m1, m2, mi, and mn, moving at an instant with the velocities v1 vector, v2 vector, vi vector, and vn vector respectively, is given by. Here, we are writing kinetic energy of the system of these particles m1, m2, mi, mn masses in that frame in which their velocities are measured to be v1, v2, vi, and vn respectively. This is not necessarily center mass frame. So what will be total kinetic energy? Summation k is equal to summation half mi vi square. Now let us try to introduce velocity of mass center. If we can denote velocity of mass center by vc vector and velocity of any particle with respect to mass center, say ith particle, by vector vi with respect to c, then we can express vi by idea of relative motion. So vi vector will be vc plus vi oblique c. So in this way, we can incorporate here the kinetic energy in terms of velocities with respect to mass center. So let us see how can we do it. Denoting velocity of the mass center by vc and the velocity of the ith particle with respect to the mass center by vi with respect to c, we can write vi vector is equal to vi with respect to c plus vc vector. So what it will be? Summation k will be summation half mi vi with respect to c plus vc, or vc plus vi with respect to c whole square. Now it is square of a vector quantity. So square of a vector quantity is self product, means dot product of the vector with itself. So that is called self product. So let us write it further. So summation k will be summation half mi vc plus vi oblique c dot, again vc plus vi oblique c. Now we can simplify it. What we get? Summation k is equal to summation half mi vc square plus vi oblique c square plus 2 vi oblique c dot vc. Here we can write vc dot vi oblique c or vi oblique c dot vc because dot product is commutative. Now we can multiply the term mi to all the terms. So what we get? Summation k is equal to summation half mi vc square plus summation half mi vi oblique c square plus this 2 and half cancel. So what you get? Summation mi vi oblique c dot vc. Now let us see to just concentrate on these three terms. Now in the first term, vc is same for all the particles. So vc we can take outside of the summation. So we can put into a parenthesis. So summation and half we can take outside. So half summation mi and vc square. Summation mi is the total mass of the system. So this we can represent half into total mass of system into vc square. And we denote the total mass of system by a letter capital M, and we always do it. Now let us see in this second term. It is you can see velocity of ith particle with respect to mass center. So it is sum of all the kinetic energies of all the particles due to their motion with respect to mass center. So that term has a great interpretation. Now let us see in the third term. VC same for all the particles. So we can take VC outside summation. So we can put these two terms in parenthesis. And as we put these in parenthesis, what we get? Total momentum of the system in center mass frame, and that should be null vector. So the third term will be null vector. So now what we get? Summation K is equal to half summation Mi Vc square plus half summation Mi Vi oblique C square plus in parenthesis summation Mi Vi oblique C dot Vc. So here half we can take outside of summation, and summation Mi and Vc square we can take outside summation. So here a quantity under parenthesis, please take care of this. Again here Vc we can take outside of summation, so it is quantity under parenthesis. As I explained, this is the total mass of system. We denote it by capital M, and this is total momentum of system in center mass, and it is null vector. So what we can do? Denoting summation Mi by capital M and substituting summation Mi Vi oblique C is equal to null vector, we get summation K, total kinetic energy system in the reference frame in which these velocities are measured, is half capital M into Vc square plus this summation half Mi Vi with respect to C square. Actually, if you see these two terms on the right hand side, this is what a mathematical term, or you can say the kinetic energy total of system can be divided into two parts. First part is due to motion of mass center, that we call it is kinetic energy due to motion of mass center of the system. If mass center is not moving, this term will be 0. And this is kinetic energy due to velocities of all the particles with respect to mass center. So it is the kinetic energy system in center mass frame. So let us write them. K due to motion of mass center, and that is K due to motion relative to mass center. Now this term K due to motion of mass center can be written as K of mass center. So due to motion, these three words we can omit, so it will be a much shorter notation. So what we call kinetic energy of mass center, because it will exist, only mass center will be moving. If mass center is not moving, this term will be 0. And of course, this is what? Kinetic energy in the center mass frame. So on the next screen, we reproduce this equation with their new names. Say here, K is equal to, again, this is total kinetic energy, is a kinetic energy of mass center plus kinetic energy in center mass frame. Now we'll discuss various properties of these two parts of kinetic energies. First we discuss kinetic energy of mass center, means kinetic energy of the system because of motion of mass center. Total kinetic energy of a system due to motion of its mass center, that is the first member of the right hand side, is also known as kinetic energy of the mass center, as we have explained earlier. So what we written here, kinetic energy of the mass center. Now this has two very important properties. What they are, let us discuss. The following two characteristics of the kinetic energy of the mass center play very crucial role in applying the energy method on a system of particles. What they are? You can think of velocity of mass center will only change when there are external forces, or we can say only external forces can change Vc. So if on a system there are no external forces, this part of kinetic energy will remain unchanged. Again, velocity of mass center cannot be changed by internal forces. So whatever the internal forces will do, this part of kinetic energy will not change. So these are two very remarkable properties or characteristics of what? Kinetic energy of mass center. So let us document them. First, in absence of external forces or the net external force, the total momentum of a system and hence velocity of the mass center remain unchanged. Therefore, the kinetic energy of the mass center remains unchanged. That is what? If there are no external forces acting on system, or even external forces are acting but the resultant is 0. Under both the conditions, total momentum of system will remain conserved and velocity of mass center will not change. So in this case, total energy of the mass center, kinetic energy of mass center will remain unchanged. Means what you can say? External forces can only change this kinetic energy. Second, internal forces cannot change the total momentum of a system and velocity of mass center. Therefore, the kinetic energy of the mass center. Means what we can say? This part of kinetic energy can only be changed by external forces. It cannot be changed by internal forces. These are the two important characteristics. On the same line, we discuss about kinetic energy in the center mass frame. Kinetic energy of a system in the center of mass frame. What is that? Total kinetic energy of a system due to motion of its particles relative to the mass center, that is, the second member of the right hand side is the kinetic energy in the center of mass frame. So this one, here we written the name kinetic energy in the center of mass frame. Two important characteristics of the kinetic energy in the center of mass frame, what they are? Actually, by external forces, we can change it. So external forces may or may not change it. But if internal forces are changing energy, they can change only this part of energy because they cannot change this part of energy. So these are the two important properties or characteristics, what they are. External forces may or may not alter this kinetic energy. Second, internal forces can alter this kinetic energy only. So again, I am revising it. This part can be changed only by external forces and not by internal forces. This part can be changed by internal forces as well as by external forces. But if external forces are not present, this part can only be changed by internal forces. So these ideas will play, what you said here, very crucial role in applying the energy methods in center mass frame. Now here, very important idea. Kinetic energy of a two-particle system in center mass frame. Actually, examinations like IIT, JEE, they are based on your understanding of the idea. They are not interested to check how much algebraic calculation you can perform. So if a question will be asked on that topic, the intention of examiner will be only what? Whether you have understood various aspects of center mass frame or not. So in most of time, two particle systems are involved in problems because they represents very simple calculation, but interpretations of properties are the same as if they are for n particle system. So here let us write kinetic energy of a two particle system in center mass frame. Again, why I am writing here, this expression is reduced to a very simple form also. Let us see how. Consider a system of two particles of masses m1 and m2. At an instant of time, the particles are observed moving with the velocities v1 vector and v2 vector. Now, we discuss another way to express the kinetic energy in the center of mass frame. Actually, in center mass frame, what will be kinetic energy? Total kinetic energy of both the particles because of their velocities related to center of mass. So we can write here summation k s oblique c means s for system, summation for total with respect to mass and state. What is that for a general system of n particle? Summation half mi vi oblique c square. So for two particle system, it will be half m1 v1 square with respect to c plus half m2 v2 with respect to c square. So it will be half m1 v1 with respect to c square plus half m2 v2 with respect to c square. Now in place of v1, what we can write? v1 with respect to c vector is equal to v1 vector minus vc vector. Similarly, v2 with respect to c vector is v2 vector minus vc vector. Let us substitute here. So denoting velocity of the mass center by vc vector, we can write what? Summation k s with respect to c is half m1 v1 vector minus vc vector whole square plus half m2 v2 vector minus vc vector whole square. So we have replaced them with the relative motion idea. Now Vc we can write. If m1 has velocity vector v1 and m2 has velocity vector v2, so Vc will be m1 v1 plus m2 v2 vector upon m1 plus m2. So let us substitute these values for Vc. So what you get? Half m1 v1 vector minus m1 v1 vector plus m2 v2 vector upon m1 plus m2. We have written expression for Vc. Similarly for the second term, that is half m2 v2 vector minus m1 v1 vector plus m2 v2 vector upon m1 plus m2 and whole square of that. For further simplification, let us take LCM here or here. If you take LCM here, so m1 v1 vector plus m2 v1 vector minus m1 vector minus m2 v2 vector. So m1 v1 vector will get cancelled. So what you get here? m2 v1 vector minus m2 v2 vector. Similarly here what you can take? m1 v2 vector plus m2 v2 vector minus m1 v1 vector minus m2 v2 vector. So m2 v2 vector will get cancelled. So what you get? m1 v2 vector minus m1 v1 vector. So let us do it. So what you get? Half m1. After LCM, what you get here? m1 v1 vector minus, m2 v1 vector minus m2 v2 vector upon m1 plus m2. How we get this? m1 v1 plus m2 v1 minus m1 v1 minus m2 v2. So what is cancelled? m1 v1 get cancelled. So what you get? m2 v1 vector minus m2 v2 vector. So this is numerator here. And all the things are same. Similarly for the second term, half m2. What you get? m1 v2 vector minus m1 v1 vector upon m1 plus m2. I will leave this verification on you. And one thing here, what we can take, that is m2 we can take common here, m1 we can take common here. So in bracket what is remaining? v1 minus v2. Here v2 minus v1. And again we know we have square of this term. So we can write here v2 minus v1 also. So what is that? Half m1 m2 v2 minus v1 upon m1 plus m2 whole square. How we can write? Because here we have whole square. So whether we write v1 minus v2 or v2 minus v1, it doesn't matter. And because why we are writing here, let us see. It is clear for the second term, half m2. We can take m1 common, v2 vector minus v1 vector upon m1 plus m2 whole square. So from this, what we can take common? We can take half common, and v2 minus v1 whole square we can take common. And if you see what is remaining in parenthesis, we'll get very simple relation, that is half m1 m2 upon m1 plus m2 into v2 vector minus v1 vector square. Now at present this expression will become appear somewhat lengthy, but this term in two particle system m1 m2 upon m1 plus m2, some product of masses upon sum of masses of two particle system, we'll encounter this term so many times. So we'll give it a name. It is called reduced mass, and we denote it by symbol mu. So, and it is a simple relative velocity. So we can write here half into mu into v relative square. So in this way you can find very simple relation for the kinetic energy of a two particle system in center mass frame. Again you can realize such kind of simple relation is not possible for three or more particle system. So now we can summarize here. The expression represented by mu is known as reduced mass, and it is what? Mu is equal to m1 m2 upon m1 plus m2. So please remember it. And for kinetic energy of a two particle system in the center of mass frame, we now have a very simple expression, and that is summation k s with respect to c is equal to half mu v relative square. Now we can see from here the problem what we have taken on introductory screen. Find maximum extension in the spring given there. So when extension is maximum, you can see both the blocks will have same velocity at that time. Their relative velocity is 0. So in center mass frame, kinetic energy system will be 0. Again we know in center mass frame, initial kinetic energy is 0. So in center mass frame, initial and final both kinetic energies are zero, so there is no change in kinetic energy of system in center mass frame. Again, what we can see further, the work are done only by F and spring force, and that we can encounter. Work done by spring force is decrease in potential energy. It is again frame independent. But let us see, when we solve this problem, we'll see all this simplicity. So in this way, we have obtained a very beautiful or very simple relation or expression for a kinetic energy of a two-particle system in center mass frame. Now, total work of pseudo forces in the center mass frame is zero. Actually, on the last one, we have taken it as a property of center mass frame. Now today we'll deduce it why it is zero. Total work of pseudo forces on all the particles of a system in the center of mass frame can be expressed as summation minus mi AC dot delta Ri with respect to C. Here mi AC with minus sign is pseudo force. What is pseudo force? Mass into reverse of acceleration of reference frame. So that is pseudo force of ith particle, and that is displacement of ith particle. Now we take displacement of such size in which AC can be assumed almost uniform. So under this interval, that is what? Total work done by all the pseudo forces. Now AC is same for all I. So AC we can take outside of the summation and dot product. So what we get here? WP with respect to C means work done by pseudo forces with respect to center mass is summation minus mi AC vector dot Ri oblique C. So AC we can take outside and dot product is commutative. So we can write here delta Ri oblique C dot AC, and AC we can take outside of the summation. So what we get? Summation minus mi delta Ri oblique C dot AC. See here. Now just concentrate. We have learned on the last one that total mass moment summation mi Ri oblique C in center mass frame is always a null vector. So its change will also be also null vector. So that is what? This quantity, that is summation, will be a null vector. So what we get? Null vector dot AC, that is 0. So in this way, we got the total work done by all the pseudo forces in center mass is 0. It is a great simplicity while using energy method in center mass frame and external forces are acting. When external forces are acting, center mass frame is a non-inertial frame, but pseudo forces in that frame, work done total is 0. So that is great simplicity. Now we concentrate on discuss another remarkable idea. Before that, let us write it. We have written it in red color. Summation W by pseudo forces in center mass frame is 0. It is so remarkable idea that I have written again in red color. Work energy theorem and center mass frame. So now we discuss work energy theorem and center mass frame. First we write general expression for a work energy theorem. The work energy theorem in any reference frame, not center mass, any reference frame, what it will be? Summation W external means total work done by external forces. Summation W internal means total work done by internal forces. Summation K final means total final kinetic energy minus summation K initial, total initial kinetic energy. So work done by all the external forces plus work done by all the internal forces is equal to change in kinetic energy of the system in that frame. The work energy theorem in the center of mass frame. Now if you want to write in center mass frame, to write work energy theorem in any frame, we have to consider work done by in that frame and kinetic energy in that frame. So what it will be? This will be with respect to mass center, this will be again with respect to mass center, this will be again with respect to mass center, again with respect to mass center. So the expression will become here. To apply the work energy theorem in the center of mass frame, consider work done by all the forces as well as the initial and final kinetic energies in the center of mass frame. In addition, it is not required to calculate the total work of the pseudo forces, as this quantity is 0 in the center of mass frame. So what is that? Summation W external with respect to mass center plus summation W internal with respect to mass center plus summation K final with respect to mass center minus summation K initial with respect to mass center. So that is work energy theorem in center mass frame. For two particle system, we can write here half mu V relative final square. This half mu V relative initial square we have seen earlier. That is, kinetic energy of a two particle system is what? Half mu V relative square. So for a two particle system, the above equation reduces to simple form. What? Summation W external with respect to mass center plus summation W internal with respect to mass center is equal to half mu V relative final square minus half mu V relative initial square. So till now, we have discussed almost every idea how we can use work energy theorem or energy methods in center mass frame. Now let us summarize it. In center mass frame, first and very important thing, total work done by all the pseudo forces will be zero. We have to consider work of all the external forces in the center mass frame plus work done by all the internal forces in center mass frame equal to change in kinetic energy in center mass frame. Again, in internal forces work done, that can be divided in two parts. One is work done by all the internal conservative forces, and second, work done by all the internal non-conservative forces. Work done by all the internal conservative forces is decrease in potential system, and that is frame independent. So it will be same as it is in laboratory frame or ground frame. Similarly, if work done by all the non-conservative forces, loss in mechanical energy as work done by friction. So it is again frame independent. So it will be the same as in laboratory frame. So these ideas will simplify our situation or problems greatly. Now we discuss all the things what we learned in few examples. The first example, we take what we had taken on the introductory screen. What is that? Two blocks A and B of masses M and capital M, connected by a spring of force constant K, are placed on a frictionless horizontal floor. A constant force F is applied on one of the blocks as shown in the figure. See here, A block, B block, its mass we assume small m, its block we assume capital M, the force F is applied, and we have to find the maximum extension of the spring during the subsequent motion. Now let us see how ground frame creates difficulty. Let us discuss it. If we use the ground frame as the inertial frame, as we usually do, solution of the problem become quite involved, as we have to calculate the displacements of the blocks at the time of maximum extension. Therefore, we prefer the center of mass frame. In the center of mass frame, the center of mass remains at rest, and we have to consider only displacements of the blocks with respect to the mass center. Actually, in center mass, it is not required to consider the net displacement blocks. We have to simply consider displacements of the block with respect to mass center. Again, we have seen that is while studying center of mass, that is the center of mass of a two particle system divide the separation between them in reciprocal ratio of masses. So it will also divide the change in separation reciprocal ratio of masses. So in this way, we can write extension, how it is shared by the masses. So displacement of block A with respect to mass center and displacement of block B with respect to mass center will be in reciprocal ratio of the masses. So that will provide very simple idea and simplicity in solving the problem. So one thing, again, in center mass frame, we have this simplicity, but in ground frame, we have to write displacements with respect to ground. For that, as I mentioned earlier, what we know, the time of the maximum extension and force, especially spring force as function of time, only we can calculate acceleration and then we can calculate displacement. Writing spring force as function of time and time of maximum extension is not possible at present because we have not studied simple harmonic motion. So we cannot do that one. So let us see how, again, in center mass frame will simplify solution here. That is the idea we have seen. And further, in addition, the initial and the final kinetic energies of the system are zero because at the initial and at the final moments, relative velocity between the blocks is zero. That is a great idea. Let us elaborate it. In the center of mass frame, the initial total kinetic energy is zero because both the blocks begin to move from rest, and final kinetic energy is also zero because at the maximum extension both the blocks must have equal velocities in ground frame, and in center mass they must be at rest. So again the relative velocity zero, so in center mass frame total kinetic energy final is also zero, so change in kinetic energy zero. Work done by pseudo forces total is also zero, so we have to consider work done by the applied force F and the spring force. Now let us see. Knowing the initial and final kinetic energies in the center of mass frame, to find the maximum extension in the spring, that is the sum of magnitudes of displacements of the blocks relative to the mass center, we should use the method of work and energy in the center of mass frame. Why? In using center mass frame, one thing, we have not to consider work done by pseudo forces. Again, work done by spring, that we have to consider total work done. We are not supposed to work done by spring on block A and work done by spring on block B. What? We have to consider total work done by spring force, that will be decrease in stored potential energy of the spring, and that can be written in terms of extension of the spring, and that we have to find. Again, to write work done by force on block B in center mass frame, we have to write displacement block B into force F, and again displacement of block B can be written in terms of extension, because we know displacement of blocks, their sum is extension, one thing, and the displacements are in reciprocal ratio of masses. Let us see how can we realize these ideas. As the mass center of a two particle system divides separation between them in the reciprocal ratio of the masses, displacement delta x1 with respect to c and delta x2 with respect to c of the blocks relative to the mass center must also be in reciprocal ratio of the masses. Thus, denoting the maximum extension by xm, we get what? This first, before writing it, let us see the situation, because we must have very clear imagination of these displacement. So let us see initial and final configurations. That is initial configuration before the force was applied, and now force is applied at the t is equal to 0. Just when the force is applied, the blocks has not moved at all, they have not acquired any velocity, so the spring is relaxed. Now in the final extension, here we know that in center mass frame, center mass will remain same. So if here center mass, here will be center mass of second configuration also. See this, C. Now if you see from here to here is the displacement block A, this one. Similarly from here to here is displacement of block B, this one. And so this displacement block is what? Delta x1 with respect to C. And this is what? Displacement of block B, that is delta x2 with respect to C. Now what we can come here, delta x1 with respect to C plus delta x2 with respect to C is what? Extension spring, that is clearly visible here. It is xm. Delta x1 plus C is what? mxm upon mx plus m. Why we can write it? Because we know their sum is what? xm. Again the ratio is what? Reciprocal ratio of masses. So simply by ratio and proportion we can write delta x1 with respect to C what? This mass into sum of upon sum of mass into total of this xm. Similarly, delta x2 with respect to C will be what? Small m xm upon m plus m. So writing these results are not difficult. Now with the knowledge of this, let us show it here. This delta x1 with respect to C is equal to m xm upon m plus m. And similarly here, delta x2 with respect to C is equal to m xm upon m plus m. And we know the force is constant. So by multiplying this displacement, this force, we can write work done by the force. Just see how simple is to write work done by the force F. And to write work done by spring force, again very simple. What? decrease in potential energy. Initial potential was 0 and final potential is what? Half k xm square. So now we have know everything, and we also know that total kinetic change is 0. So every term what we had to substitute in work energy theorem in center mass frame, we know. Now the task remains is just to substitute these values. So but first write initial and final kinetic energies. So delta k initial with respect to C is 0, and that is summation k final with respect to C is 0 that we have done earlier. Work done by various forces. What are the forces? Gravity and normal reactions. And the applied forces are the external forces. And the spring forces on the blocks are the internal forces. In addition to these external and internal forces or physical forces, pseudo forces also act on the blocks due to acceleration of mass center. Because this unbalanced force will cause the mass center to accelerate. So we have to consider pseudo force also. Gravity and the normal reactions do no work as displacements of the particles on which they act are perpendicular to the respective forces. Total work of the pseudo forces are 0 in the center mass frame. So only the applied force F does work from the external force. So among the external force, which force does work? Only the applied force F. And this is very simple to write. W external, C is what? Force into this displacement. So F delta x2 oblique C. So what will be? F small m xm upon m plus m. So total work done by external forces we have written. Now we write total work done by internal forces. Work done by pseudo forces, we know that is 0. So total work done by the spring forces, that is the internal forces, is equal to the decrease in the stored potential energy of the spring. So it will be summation W internal with respect to C is equal to initial potential energy, spring was relaxed, and final minus half k xm square. So what you get? Minus half k xm square is the work done by internal forces. Now we will write all the terms, this one, this one, this one, and that, and we substitute it in work energy theorem. Expressions for the kinetic energies and total works done by the external and the internal forces, we are reproducing here what they are. Summation ki oblique C means total initial kinetic energy center mass frame is 0. Again, total final kinetic energy in center mass frame is 0. Total work done by external forces in center mass frame, we have written F small m xm upon m plus m. And total work done by internal forces in center mass frame is minus half k xm square. Now we substitute these values in work energy theorem for center mass. Substituting the above expressions in the work energy theorem in the center of mass frame, we get, first we write work energy theorem, summation W external oblique C plus summation W internal oblique C plus summation K F oblique C minus summation K I oblique C. What is this? Total work done by external force in center mass frame. That is total work done by internal force in center mass frame. That is total work done, total kinetic energy final in center mass frame. That is total kinetic energy initial in center mass frame. Now we substitute these values. So for that we have this F small m xm upon m plus m. For this we have minus half k xm square, 0 minus 0. So that is 0. And it is very simple from here to write what is xm, and you can verify. So that is expression for xm. Now you can see. You can think that this solution was quite lengthy because we had to think so many things. But after solving few problems, all the thoughts, you'll become habitual of thinking all these things. So you can think all the ideas very quickly in fraction of a second. And finally, you write this theorem and put the value, and you can solve this problem within 1 or 2 steps. So that is what is going to be in exam. Now let us discuss next problem of almost similar kind. Example 2. Two blocks A and B of masses ma and mb connected by a spring of force constant k placed on a frictionless horizontal floor are simultaneously given velocities u and ub as shown in the figure. Say here. Instead of applying force, the blocks are given simultaneously these velocities. This block is given velocity ub and this block is given velocity ua, and it is seen that is ub is somewhat larger. So the spring will initially extend. What did you find? Find the maximum extension of the spring during the subsequent motion. Again, here by the same logic, almost use of center mass frame will provide somewhat simpler solution. Because in center mass frame, one thing, no external forces are doing work. First thing, there are no pseudo forces. If they were, their work done zero. Only we have to consider total work done by the internal force, they are spring force, and that can be written in terms of the unknown quantity, which is as exchange in spring, decrease in potential energy. One thing. And initial kinetic energy you can write in terms of relative velocities. And final kinetic energy must be zero, because at the time of maximum extension, both the blocks will be moving with the same velocity, and that velocity is center mass frame. So in velocity of center mass. So in center mass frame, both the blocks will be at rest finally at the time of maximum extension. So in center mass frame, total kinetic energy final must be zero. So let us see how we can simplify or solve this problem. The situation at hand can be analyzed easily in the center of a mass frame, employing methods of work and energy. Initial and the final kinetic energies of the two-particle system in the center of mass frame, and we can write the expression what? K system with respect to C is half mu means what? Product of masses upon sum of masses, ma mb upon ma plus mb into v relative square. So we can write initial kinetic energy. Summation ki with respect to C is half ma mb upon ma plus mb ub minus ua square. That is initial kinetic energy. And final kinetic energy, summation k final with respect to C is 0, because the relative velocity at the maximum extension will be 0. So we return both the kinetic energies. Work done by the internal spring force is equal to the decrease in the potential energy stored in the spring. So we can write here that is frame independent. Therefore, what it would be? Summation W internal with respect to C is 0 minus half k xm square. So it is minus half k xm square. No external forces are doing any work. So now we are ready to put the values in work energy theorem. Substituting these values in the work energy theorem in the center of mass frame, we get what? Summation W external with respect to mass center plus summation W internal with respect to mass center is equal to summation K final with respect to mass center minus K initial with respect to mass center. Here this is 0, and for this we substitute this. For this we substitute 0, and for this we substitute this, and let us see. 0 minus half k xm square is equal to 0 minus this. And by solving this, you can easily find what is xm. So xm is ub minus ua square root mmb upon k into ma plus mb. So that is what maximum extension. Now you can see how easily you can obtain here this by using center mass frame. Now we'll take a very interesting problem on collision. Actually, if it is asked the loss in kinetic energy in collision and coefficient of restitution is given, now you can realize if you want to deduce a general expression of loss in kinetic energy in a collision in terms of coefficient of restitution in laboratory frame, you realize what great difficulty you'll find. But this idea provides very, very simple and beautiful solution for that. Let us see. Example 3. Two balls A and B of masses ma and mb moving with the velocities ua and ub in the same direction make a head-on collision as shown in the figure. Coefficient of restitution for the collision is E. So that is what situation before collision. Now we assume after collision denote velocity by VA and VB. What we have to calculate? First one, find the energy utilized in the deformation process. So we have to see what is energy utilized in deformation process. It is energy required to deform the bodies from the beginning of collision till the maximum deformation. Because after that restitution period will begin. So let us first define or identify this. Energy utilized in the deformation process is the total energy utilized in the deformation from the beginning of the collision to the instant of the maximum deformation. So let us see how we can calculate it. External forces are absent and the deforming forces are the only internal forces. Therefore, the total work done by the internal forces, that is the deforming forces, is utilized in changing the total kinetic energy in the center of mass frame. Just recall. That is, if there are no external forces, only internal forces can change the energy in center mass frame. So in collision there are no external forces. So our internal forces are the deforming forces. So work done by them will be what? Change in kinetic energy center mass frame. So that's so simple idea. Summation W external plus C plus summation W internal oblique C is equal to summation K final oblique C minus summation K initial oblique C. That term is 0. And we have to find this term. So this is what? Summation K final oblique C minus summation K initial oblique C. This is what? Half mu V relative final square minus half mu V relative initial square. And we have to calculate this one. Okay. So, and we know at the time of maximum deformation V relative is 0 because both the blocks are moving with the same velocity as that of center of mass. So what is that? Initial and the final kinetic energies. Summation K initial we can write very easily half mu V relative initial square. So that is half MA MB upon MA plus MB into UB minus UA or UA minus UB, what you write, because you have to put a square. So it doesn't matter what the order is there. Summation K final with respect to C. Half mu V relative final square, and that should be 0 because final, when the time of maximum deformation, both the blocks have the same velocity as the center mass has. Substituting the above expressions in the work energy theorem, we get what? We have to calculate this quantity. So that is W internal conservatives, that is this quantity, UB, UA minus UB. Now here, of course, if you take this and 0 minus this, you get negative. But here, just my purpose is to find its magnitude. So that is what loss in kinetic energy. Actually, you have to find, energy utilized in deformation process. Actually, this energy is what work done is negative. Of course, you can see from here. But it is asked energy utilized. So we have to represent this magnitude. So this amount of energy is utilized in the deformation process. Now we are come on the B part. That is very interesting. What? Find the kinetic energy lost in the collision if coefficient of restitution is E. What the idea we can think here? Again, there are no external forces. So kinetic energy of mass center will remain unchanged. One thing. So what is going to change? Only kinetic energy center mass frame. And this can be changed only by internal forces. And what are internal forces? Deforming forces. Now think again. There are no external forces. So internal forces can change only what? The kinetic energy center mass frame. So total change in kinetic energy is any frame will be here equal to change in kinetic energy center mass frame because kinetic energy of mass center is not going to change. And change in kinetic in center mass frame can very easily be calculated, because for that we have very simple formula. What? Half mu v relative square. So let us see. External forces are absent and the deforming forces are the only internal forces. Therefore, the total work done by them is equal to the loss in kinetic energy. This is very important idea. Let us express this mathematically. What is that? Summation, that is delta K, is equal to summation W internal conservative. Again, think here. Total change in kinetic energy or loss in kinetic energy here is the total work done by all the internal forces, because external forces are not doing any work. As the external forces are absent, kinetic energy of the mass center remain unchanged. Therefore, center of mass frame should be preferred, because only there is change in kinetic energy in center mass frame. Substituting W external with respect to C in the work energy theorem in the center mass frame, what we get? Delta K is equal to summation W internal with respect to C is equal to half mu V relative square final minus half mu V relative square initial. Just see how simple thing is. The only thing is what? We have to substitute the values. Initial and final kinetic energies. Summation K I initial half mu UA minus UB whole square. Say question 2. And summation K finals with respect to C is half mu VA minus VB whole square. Here we are denoting velocities after collision by VA minus VB. Substituting VA minus VB is equal to minus E UA minus UB. That is idea of coefficient precipitation. Very important. What we get? This summation K final with respect to C is half mu E UA minus UB square. So now we are ready to write delta K loss in kinetic energy. From equation 1 and 2 and 3 we get delta K is equal to half mu, this is E square minus 1 UA minus UB. That is loss. Means here this, you can see if you subtract from this quantity half mu UA minus UB, can command what is remaining? E square minus 1. So here we get very simple relation for the loss in kinetic energy in center mass frame. And this is also loss in kinetic energy in laboratory frame. Actually, in this way, we have seen that how center mass presents a very simple idea in solving some of the situations. And I'll conclude today's lecture at this juncture of time. In the next class, we'll meet and we discuss about how can we apply Newton's laws, energy method and momentum method on variable system of particles. Till then, thanks for patient listening. We'll meet in the next class. The words of a language, as they are written or spoken, do not seem to play any role in my mechanism of thought. The physical entities which seems to serve as elements in thought are certain signs and more or less clear images. Albert Einstein.